Picture this. It's the autumn of 1666, out in the super quiet English countryside. A 23-year-old guy is just sitting alone in a garden. He isn't famous, and honestly, he isn't even completely sure he wants to be a scientist. The world outside is terrifying right now. A devastating plague is sweeping through London, and all the universities have totally shut down. But in this quiet, forced isolation, something is about to happen that will fundamentally change how humanity understands the universe. And it wasn't some dramatic lightning bolt of genius, but a simple apple falling from a branch. Welcome to This Explainer, where we're diving into the incredible story of Isaac Newton and the universal pull of gravity. So, you really gotta wonder, right? How exactly did one guy, literally just sitting in a garden, unlock the gravity of the entire universe? It honestly sounds like a complete myth, but the reality is far more fascinating. We're gonna look at how a simple falling apple led directly to humanity predicting the motion of absolutely everything in the sky, from the exact equation he created, all the way to how you can calculate the gravity of any planet in the universe yourself. To really get this, we have to start with a tale of two physics. See, before Newton came along, the universe was kind of this divided place. We had two completely unconnected mysteries. On one side, you had earthly physics. The Italian scientist Galileo Galilei had already proven that falling objects on Earth accelerate at a predictable rate. You drop a heavy stone and a light one, they hit the dirt at the exact same time. On the other side, though, you had celestial physics. The German astronomer Johannes Kepler proved that planets orbit in these beautiful, precise mathematical curves. But here is the crucial point. Absolutely no one had connected these two worlds. The rules of the dirt were definitely not the rules of the stars. Back in 1665, Newton was a student at Cambridge when the Great Plague hit. The university shuts down, forcing him into this quiet exile at his family's farm, Woolsthorpe Manor. Now, instead of taking a vacation, this turns into 18 months of just unprecedented intellectual productivity. He is totally alone, no professors, no distractions, just tackling the absolute hardest problems in physics. Then comes autumn 1666. He's out in the orchard and he watches an apple fall, and despite the whole cartoon legend, no, it didn't actually bunk him on the head, but it did spark a profound thought. He started wondering, how far up does this pulling force actually go? And that brings us to the radical leap. He asked this crazy question: what if the force pulling the apple is the exact same force holding the moon in orbit? I mean, for 2 millennia, thinkers just assumed the stars and planets were untouchable, perfect things operating on completely different rules from our gritty, earthly reality. Newton threw that right out the window. He basically hypothesized that the moon is falling toward Earth, exactly like the apple. The only difference? The moon is moving sideways so incredibly fast that as it falls, the Earth's surface just curves away beneath it. It is perpetually falling and perpetually missing the ground. Such an incredibly elegant idea, but actually proving it, that was going to take some serious work. Because as it turns out, gravity wasn't just solved in a single afternoon. Back in the 1660s, Newton gets this flash of intuition, does some early testing, and then, well, he just kind of sets it aside. He gets distracted by other projects and literally doesn't return to it for nearly 2 decades. It wasn't until the 1680s that his buddy, the astronomer Edmund Halley, yeah, the famous comic guy, basically begged him to formally write his theories down. And finally, in 1687, Newton published the Principia Mathematica, officially turning that little flash of intuition into hard, provable mathematics. So let's actually get into decoding the equation. Newton's law of universal gravitation says something absolutely breathtaking. It states that every single object in the universe attracts every other object. The gravitational force between two things is directly proportional to the product of their masses. So double the mass, you double the pull. But, and here's the catch, it is inversely proportional to the square of the distance between them. That means if you double the distance separating two things, the pull drops to just 1/4 of its original strength. This math perfectly dictates how things pull on each other across the entire void of space. Now, if we want to figure out surface gravity, the force that determines what you'd weigh standing on another planet, we can actually use a highly simplified version of this law. Since we're just calculating the pull on, say, a 1 kilogram test object, like yourself standing on a scale, your mass neatly cancels out of the equation. You literally just need 3 steps. Take the planet's mass, divide it by the square of the planet's radius, then multiply that by g, which is the gravitational constant. That's it. Just 2 numbers unique to a planet, its mass and its radius, and you've got everything you need. Let's put this into practice by weighing the worlds. Let's start with our baseline, Earth. We combine its mass and radius, and we get a surface gravity of roughly 9.8 meters per second squared. That is the steady, familiar downward pull keeping you in your chair right now. Okay, now look at Mars. It is way less massive than Earth and has a much smaller radius, which yields a surface gravity of just 3.7. But what about Jupiter? It's a gas giant with over 300 times the mass of Earth. You'd think the gravity would be hundreds of times stronger, right? But remember step 2? We divide by the square of the radius. Jupiter is incredibly massive, sure, but it's also incredibly wide, which totally offsets that extreme weight. Its surface gravity works out to 24.8. To make this a bit more real, imagine a 70-kilogram astronaut. On Earth, they feel exactly like 70 kilograms. But on Mars, because the pull is well under half of Earth's, they'd feel like they weigh closer to 26 kilograms. Literally the ultimate weight loss program. They could just bound right across the surface. Jupiter, on the other hand, well, if they could somehow stand on its gaseous surface, that 24.8 meters per second squared means they'd feel about 2.5 times heavier. They would seriously struggle just to stand up. Hand the equation at mass and a radius, and it tells you exactly how hard that world pulls. Which brings us to the ultimate proof in the stars. You know, when Newton first published this law, it faced massive pushback. Critics, especially the followers of French philosopher René Descartes, just flat out rejected it. To them, the idea of a force reaching across millions of miles of empty space without anything physically connecting the bodies, it sounded totally absurd, like invisible magic, not rigorous science. And the wild part is, Newton himself was pretty uneasy about this too. He could mathematically describe exactly how gravity behaved, but he straight up admitted he had zero clue what gravity actually was. That deeper mystery would remain unsolved for centuries. But Newton's ultimate vindication didn't come from philosophers arguing in a room. It came from the sky. Fast forward to the 1840s. Astronomers noticed the planet Uranus is moving strangely. It's totally deviating from its expected orbit. Now, instead of throwing Newton's law in the trash, two mathematicians, Urbain Le Verrier and John Couch Adams, decided to trust the math. They ran Newton's equations in reverse to figure out exactly where a hidden massive object would have to be sitting out in the dark to tug on Uranus like that. In 1846, telescopes pointed to those exact coordinates and boom, there was Neptune, a brand new planet discovered not by randomly looking through a lens, but by pure mathematical calculation. How incredible is that? This single law guided all of science for over 200 years. Eventually, yes, Albert Einstein comes along with general relativity, and he finally explains that invisible magic by showing gravity is actually the curving of space-time itself. But here's the thing. Einstein didn't erase Newton, he just absorbed him. Even today, for almost everything we do, launching satellites into orbit, sending rovers to Mars, calculating planetary weights, Newton's equation remains perfectly accurate. We are literally still relying on the math born in that English garden. That pole connects you, mathematically and precisely, to every planet, every moon, and every star in the universe. Just let that sink in for a second. The next time you feel your feet planted firmly on the ground, realize that the exact same mathematical rules pulling you down are reaching across the void, locking the entire solar system together. Newton didn't just explain an apple falling from a tree, he explained the mechanism of everything. So armed with just a mass and a radius, what other invisible worlds could you weigh today?